Right, so I'm going to talk about all the things that happened in 1969, and my title, 1969 and all that, comes from my favorite history book, and this was written in the 1930s, a long, long time before all the horrible history books came along. And it had this title, 1066 and all that, and the second part of it, all the parts you can remember, including 103 good things, 5 bad kings, and 2 genuine dates. Now, I take issue with the 2 genuine dates because I think a third date should be added, which of course is 1969. Now, Sellers and Yateman, who wrote this, wrote it, as I say, in the 1930s, so they couldn't predict how marvelous 1969 was going to be, with all the wonderful things that actually happened. Well, I was 11, and I was going to go to secondary school, so you can tell how old I am now. Don't you think I've aged well? Manchester City won the FA Cup. Is that a good thing or a bad thing? I can never tell. I'm never sure. Anne Jones beat Billie Jean King to win the Wimbledon final. Oh, that seems such a long, long time ago when an English woman won. And Murray Gell-Mann won the Nobel Prize for Physics, classification of elementary particles, and so the discovery of quarks. That was going on. But for me, the most important thing that happened 50 years ago was actually, it was the birth of the field of planetary sciences. Now, planetary sciences is the study of the origin and the evolution of the solar system. So it's trying to understand where we came from. How did the sun get here? How did the planets form? All that sort of thing. And so there were lots of discoveries, lots of things that all came together that year. And the first thing that happened was in February, a huge meteorite fell called Allende. Now, meteorites are named more or less after the places they fall. And Allende is in northern Mexico. It's about 1,000 miles from Houston. So just a short plane ride. Now, there was some stuff going on in Houston in preparation for something that was going to happen later on in the year. And so there were loads of scientists and engineers in Houston. And so what they did was they hurtled over the border when they heard about this huge meteorite fall. And they collected loads of it very quickly. And very quickly it was realized what type of meteorite it was. And it was shown that it got these, I showed you. That's a picture of it there. And up here, you can see there are some sort of odd-shaped patches, and there's a big one on the top there. It looks like a bird dropping, but it isn't. It's a strange-shaped patch. And these had been seen in other meteorites like Allende, but nobody really knew what they were. They were rich in minerals. They got minerals in them that were rich in calcium and aluminium. So they were known as calcium and aluminium rich inclusions. And when they were bigger in Allende than in any other meteorite. And what they found when they looked at these, and that top picture is a piece of Allende that's been sliced very thinly to look at under a microscope. They found these were a very irregular shape. And because they were made of these minerals, rich in calcium and aluminium, those sorts of minerals melt and boil at incredibly high temperatures. They're the sort of materials that make ceramics, that make the inside of an oven, for instance. And so what actually was understood from these was that they were formed very, very, very early on as the solar system came into being. So we'd already sort of got the idea that the solar system came from a turbulent cloud of gas, mainly hydrogen, and dust that was really active active, and the grains collided together, and the dust went to make the sun, the gas went to make the sun, and the dust formed the planets, and some gas went to form the gas giants, and they all moved around, and asteroids were zinging backwards and forwards, and it all took a certain length of time. And this was 4,567 million years ago, 4,567 million years ago. And when scientists started to look at the bits inside this meteorite, inside Allende, what they found was that the minerals were slightly different. And this is the graph on the bottom. Don't need to worry too much about the detail. You just need to be able to see the yellow spots. And you need to be able to see that yellow spots are here and not on that line there. Now, this is a graph showing oxygen. And up until this time, it was believed this cloud of gas and dust was really, really hot. And if you get this cloud really, really hot, everything gradually becomes the same sort of composition. It equilibrates, okay? And everything on the Earth, anything that's got oxygen in, so the atmosphere, the rainwater, your blood, all these things with oxygen in, their oxygen composition lies on this line called the terrestrial fractionation line. And if it's true that the cloud was all hot and well mixed, homogeneous, then all those yellow spots that came from Allende should also have lain on that line. And they don't. And what that showed for the first time was that the solar nebula wasn't mixed up. It had different clumps in. And so scientists started to try and think, well, what do those clumps mean? And the next thing they managed to do was to find that they had aluminium and magnesium in them, which were of a certain age. And they could show that these strange patches in Allende were formed about, well, we call this the year dot when they were made. They were made about 3 million years before anything else. So those irregular patches are the oldest things in the solar system, which is pretty amazing. But even more amazing was the other things they found in Allende. It's full of diamonds. Tiny, tiny, tiny diamonds, really tiny, titchy diamonds. And those diamonds have got xenon in. And again, it's this thing about isotopes, which we had for oxygen. Elements come in these sort of different brands, different masses. And the xenon in these diamonds was really, really unusual. Still not entirely sure where it's come from, but it's believed to have come from something that happened just as our solar system was forming. Maybe a star became a supernova and there was a pulse of energy into that cloud. And what that did, that pulse of energy from a supernova, could have produced diamonds from the dust. And those have been swept into the cloud and mixed in to the dust that formed the parent body, the asteroid that Allende came from. So one of the first things, at the bottom it says Allende and me. And one of the things that I worked on very early on when I was still a PhD student was trying to understand the carbon in this particular meteorite, because that was my speciality. Now, bearing in mind that Allende weighed 2 tons, 2,000 kilograms when it fell, I was given, as a student, I had like half a teaspoonful of Allende powder, powdered rock, to do my experiments on. My very first experiment, I took 18 milligrams, so a very tiny amount of Allende, and I put it on a little metal dish. and put it in a chamber. And what I was going to try and do was clean up, get rid of any contamination. And I turned the vacuum pump on, and whoomph! It went straight down the tubes. And I was so mortified. It was, oh, what am I going to do? How am I going to tell my boss? Now, my boss was Colin Pillinger, who, I don't know if many of you remember him from Beagle 2. And he just looked at me and he said, "Don't do that again." No, Colin, I won't do that again. Promise. So that was my interaction with Allende. The next thing that happened, well, no, not the next thing, but the next thing I'm going to talk about, was another meteorite fell in 1969, another really big one called Murchison. Now this has got the same sort of things in as Allende, but it's much, much darker, more finer grained. And it's actually full of organic compounds. It's full of things like amino acids. Now, this fell in a farmyard, and it actually fell in manure. And so you might think, well, we can tell where all those amino acids came from then, didn't it? It came from the byproduct of a cow, let's say. But it didn't. Those amino acids, actually, and the other organics in there, came from interstellar space, the space between the stars. Now, these particular organics, they've got carbon in and hydrogen. And hydrogen comes in two brands. It comes with a mass of 1, which is hydrogen, and it comes with a mass of 2, which is deuterium, or heavy hydrogen. And the organics in Murchison had got lots of deuterium in them. And the only way they could have been produced was by chemical reactions between molecules in the interstellar medium that had got their energy from radiation and from very slow reactions. So these came from interstellar space, which again had been mixed in to this dust cloud. The second thing that was special about Murchison was, again, it had got these presolar grains in, this time not diamonds, but grains of silicon carbide, which is carborundum, which is what you get on sandpaper as an abrasive. So not very exciting, you might think. But again, it got really strange xenon in it, really, really strange. And it was the sort of xenon that looks at it as if it had been made by a star that was actually burning carbon. And it was a star which was going through something called the S process. And the stars that do that are like red giants. Now, our star is a G star. Red giants are huge, huge, much bigger than ours. And so this has come from a star that is going through different sorts of reactions than our star. So again, it's come from somewhere beyond the solar system and got mixed in with everything. Now, the way we can analyze the diamonds and the silicon carbide is because you can't see them because they're too small. So what you actually have to do is you take a chunk of the rock and you dissolve it all away in really, really strong acids, hydrochloric acid, nitric acid, hydrofluoric acid, really nasty stuff. And you dissolve about 99.9% of the main part of the rock away. Now, some of our collaborators in America did all that chemistry, and they sent us these few precious grains of material for us to analyze. And what happened with some of those grains, what we did, the way we analyze them, is we burn them. So heat them up with oxygen and burn them to carbon dioxide, and then measure the carbon dioxide. And so I was doing one of these experiments, and I was doing it with a colleague called Peter. Now, this was, I think, October, November time, 1982. And I had just submitted my PhD thesis. So I hadn't had my viva yet, so I hadn't got my PhD, but I'd written my thesis, I'd submitted it to go to the examiners, and I was waiting to do my viva. And so in between time, Colin said, right, I'll employ you on a short contract just until we know what's happening with your viva, and then, assuming you pass your viva, we'll give you a longer contract as a postdoc. So I thought, that's great. I'm not a student anymore. So I was working on this experiment with these grains with Pete. Pete was a postdoc, he was older than me, and he was a bit bossy, and I'm a bit bossy. And although we're really, really good friends, still really good friends, I was sick and tired of being bossed around by him because I wasn't a student anymore. I was a postdoc, and he was only a postdoc. So we were in the middle of doing this experiment, and he said, look, I've got to go to the dentist. Can you wait for me till I come back before we do the next step? Because we were going to try something new. We were going to try and purify our carbon dioxide using a very, very fine powder, and we were going to freeze our carbon dioxide onto that fine powder. So he said, so don't do it. Don't. Till I come back from the dentist. And I thought, well, he can't boss me around anymore. I'm going to do it. So I opened the valve, I opened the tap to let the gas onto the pink stuff. And then I opened this very fine grain stuff. And then I opened the tap to let it into the mass spectrometer, which was under vacuum. And woof! All the fine grain pink stuff went into the mass spectrometer. And I went, oh, rude word. And Colin, whose office was just off the lab, he came in to say, what's going on? And I said, all the Poropac-Q's gone down the flight tube, Colin. And he just went, you're fired, get out of my sight. And it's like, okay, Colin, I won't do it again. Too late, you've done it once, go away. So fortunately, you know, after Pete came back and we took the mass spectrometer to pieces and we spent nearly a month cleaning all the pink stuff out of the flight tube, Colin relented and re-employed me. But oh, it was just like, oh no! So that's my memory of Murchison. Not so good. And here's Comet 67P, which was from 2014. The reason this is here is that in 1969, Comet 67P was first observed. And it's called Churyumov-Gerasimenko, after the two people who observed it, Dr. Churyumenko and Mrs. Gerasimov. I think I've got that the right way around. And they were working at a telescope in what is now Kazakhstan. And they were looking at asteroids. They weren't looking for comets. And they took this particular plate, this particular night, so it was on these great big glass plates. And when they looked at it after it had developed the next day, they could see this streak. And they tracked it back and they realized its trajectory was that of a comet, and they reported it. And that was the first observation of 67P, which became the target of Rosetta's very successful mission. I can only survive a certain amount of that. But, you know, I had been involved to the extent, you know, that I was doing scientific advice to the science team, to my husband, Ian Wright, who was the prime investigator, the principal investigator of the Ptolemy instrument. And he'd been working for, almost his entire scientific career getting to this comet. So I was very, very pleased that it had landed. And it's like, yeah, and we're still working. We're still working on the data that came back from that, which is absolutely fantastic and a really great experience. And just so fantastic to be part of that. And again, what we've learned from this comet is that we've learned about the range of different organic species that are in the comet, which, along with the water, came to the Earth to deliver the building blocks of life. So, this is another part of the history of what's been going on since 1969. And so there's one more thing as well. Oh no, there's two more things. Two more things, all right? So you're going to be hearing tomorrow from Dr. Katie Joy about meteorites in Antarctica, because she's leading British expeditions to Antarctica. Now, I went to Antarctica in 1988 as part of an American team. And this was heritage that came from a Japanese expedition in 1969. And these glaciologists were trying to track the movement of a glacier. And what they found was they found 9 meteorites. Now, the ice, as you can see up here, is very clear. It's, there's no trees, there's nothing else. And the rocks that sit on top of the ice, there aren't many of them, but as long as you're not at a moraine, which is the edge of the glaciers, more or less anything that's on top of the ice is a meteorite. Now, in 1969, we didn't know that, and this team of Japanese glaciologists found these rocks, took them back, and they were meteorites. And they weren't one meteorite that had broken into 9 different fragments. They were 9 different types of meteorite. So they'd come from 9 separate asteroids. So they'd been brought together, we understand now, by how the ice was moving. And that's what makes Antarctica really special. So there's now, I think, about 50,000 meteorites that have come from Antarctica out of a total of, 55, maybe there's 55,000 out of a total of 60,000, I can't remember. But a huge number of the meteorites that we have to study have come from the first recognition that Antarctica is a freezer full of meteorites. And that came from 1969. And you might think, well, why do we keep wanting more and more and more meteorites? Surely one meteorite's just like another. That is not true. Meteorites, this one here is a meteorite from the moon. And when you look at the Apollo rocks, it looks just like them. It's got the silvery white crystals in that make the highlands. It's got the black stuff that makes the mare. It's got the same gases trapped in it that were found in the Apollo rocks. It's a rock from the moon. And so we know the moon's got craters on it. Something came down, made a crater on the surface of the moon, threw off rocks, and some of them landed on the Earth. And we know that because we can compare them with the Apollo rocks. But we've also got rocks from Mars, like this one and this one. And although we've never sent astronauts to Mars yet, we can recognize these rocks because they've got the same gases in that we know is in Mars's atmosphere from what we've learned about Mars from space probes. So Antarctica has opened up a real treasure chest of new meteorites. And in Manchester, I guess most of you are sort of relatively from around here, I don't know. But Katie, as she'll tell you tomorrow, has been to Antarctica, collected some meteorites and brought them back. And they're sitting in Manchester at the moment, waiting to be classified. It's really exciting. But talking of Mars, and this is almost the last thing that I'm going to talk about, the week after, the 3rd week in July, or the last week of July, 1969, the final week of July in 1969, something really, really exciting happened. And that was 2 spacecraft, Mariner 6 and Mariner 7, flew past Mars. And for the first time, we got pictures of Mars which showed it had a polar ice cap. And we saw pictures of a few of the craters. And we got data back that showed it had got an atmosphere. And this was the first intelligence that we'd got that Mars was going to be this sort of interesting rocky planet. And so that was in 1969 as well, when we started to open up the study of Mars. Now, I can't pass by without reporting that something else happened in 1969, which was, of course, the founding of my institution, the Open University, by Harold Wilson. Open access, open to people's places, methods, and ideas. That's what we are. And this is why I'm here as well, because the Open University, we have the biggest planetary science group studying. Don't let the Manchester people pretend it's them. It's us, we at the OU. Because we have a mixture of physicists, chemists, biologists, astronomers, engineers, technologists, scientists. We build instrumentation to go into space. We analyze the data that come back, and we analyze the meteorites from space. And we do that in our beautiful campus at Milton Keynes, and this is our building there. So, and that's for any OU students who are here, that's Walton Hall, which is the post office box address for them. So, to summarize then, what happened in 1969, apart from the founding of the Open University, which is university education for all? We've got these momentous discoveries that led to the development of planetary sciences. We had Allende, which gave us for the first time this time scale, the chronology, the history of the solar system. We had Murchison showing for the first time that there were extraterrestrial organic samples. We've got the treasure chest of new meteorites from Antarctica. We've got a new comet that's going to be the focus of a really exciting mission. We've got Mars, and we know there's volcanoes, there's water, maybe there's life there. What else could you ask for any year? What else could you possibly want to help you understand the origin and evolution of the solar system? We got the Apollo rocks. Fantastic. Because that showed for the first time the relationship between the Earth and the Moon. It helped us understand how the Earth was formed as well as how the Moon formed. It helped us understand planetary processes. And of course, hugely significant in that was that big dish that is not quite hidden by clouds. So I just want to thank you all for listening, for celebrating 50 years of planetary sciences with me, and of course, 50 years definitely of Apollo here at Jodrell Bank. Thank you very much.